Hi, good morning, dear students. Today we are going to discuss one problem and related to the convergence in LX. And we have already discussed the definition of norm convergence and strong convergence. Okay, just to recall what is norm convergence and what are uh, strong convergence. Okay. Now, in this case, we are going to prove strong convergence need not imply non-convergence. Okay. For this, we have to prove, suppose there exists some sequence xn such that for non-convergence, it is a norm of suppose an converges to a. This is norm convergence, and strong convergence means anx minus ax norm of this tends to 0 as n tends to infinity. Okay, so here we are going to prove anx converges to ax, and but an not converges to a. This is what we are going to prove. So here consider the projections in L201 defined for any epsilon n greater than 0. We define p epsilon n f like this. Okay, this is equal to f of t. F of t means any linear function in L201. Okay, any L201. L201 means square integrated functions. Okay, so our f is belongs to this one. Okay, and p epsilon f equal to f of t for t less than epsilon. Okay, let's look at one example. If you take some f of t, I am defining f of t is equal to some 2. Okay, constant function, therefore clearly square integrable. Therefore, this belongs to L201. And what about suppose you take epsilon n? Epsilon n is greater than 0. Epsilon n is equal to some 1 by 2. Okay. Now, what is P epsilon and F? That's equal to whatever the graph of F of t. F of t is actually 2. Between 0 1, it is 2 means suppose this is 1 and this is 2. Okay, this is the graph of F of t. And P, what about P epsilon and F? P epsilon and F means this is actually epsilon F equal to F of t for t less than. So for t less than 1 by 2, it is F of t. Therefore, graph will be like this. For suppose this is 1 by 2, and for t less than 1 by 2, this is actually this is 2. This is 1 and this is 2, f of t. Okay, for all other points this is 0 for all other points. Suppose epsilon n is equal to some 1 by 4, then what happens? Suppose this is 1 by 4, f of t is this one, and for all other points this is equal to 0. If you look at if epsilon n tends to 0, the value of p epsilon f becoming 0 is greater than 0. Okay, if you consider suppose some if epsilon n is equal to some 1 by 10, okay, then the portion become suppose this is 1 by 10, then by portion, okay, this is f of t, all other terms are 0. So if this epsilon n reaches to 0, then this our p epsilon n f is actually tends to 0. Okay, so if the sequence of positive real number epsilon in closed interval 0 1 is such that epsilon n tends to 0 as n tends to infinity, then p epsilon n f is tends to 0. Hope this is clear. Okay, as epsilon n tends to 0, okay, the value of p epsilon n f is f of t if t less than epsilon n. Okay, for all other points it is 0. So the terms with 0 value of p epsilon f is greater than the non-zero values. So p epsilon n tends to 0 as n tends to infinity, and this is true for all f belongs to L2 of 0. Okay, that means p epsilon n tends to 0 in the strong sense. Okay, here anx minus ax. Okay, anx converges to ax. Okay, so here Pnf tends to 0, and this you can write as 0 of f. Okay, and therefore Pnf converges to 0 in the strong sense. Now we are going to prove P epsilon n is not uniformly converges to 0. Okay, for proving this, we have to prove P epsilon n minus 0 is not tends to 0 as n tends to infinity. Now, what is P epsilon n? This is norm of P epsilon n is equal to supremum of norm of f of n, norm of f equal to 1, P epsilon n f. Okay, norm of P epsilon n f. Now, what is norm of P epsilon n f? And that's equal to this is square is equal to integral 0 to 1, this one. Why this one? Our space is L to 0, 1. So norm is, what about norm? Norm is 2 norm. Okay. Here P epsilon n f under 2 norm. Okay. And therefore this one. Okay. Uh, and this is equal to this integral, you can split this in 0 to 1 as 0 to epsilon n, then epsilon n to 1. Okay, now for epsilon n to 1, the value of p epsilon n f is 0. Therefore this is equal to this one, and but this is less than or equal to plus epsilon n to 1 mod f of t whole square dt. Therefore this is less than or equal to this one, and but this is actually norm of f square. Okay, so if you take positive square root, we get a norm of p epsilon n f whole square is less than or equal to norm of f square, which implies norm of p epsilon n f is less than or equal to norm of f. Okay. Now, if you consider f belongs to L to 0, 1 with the norm of f equal to 1, then clearly norm of p epsilon n f is less than or equal to 1. Now we are going to prove there exists a linear function f such that p epsilon n, norm of p epsilon n f is equal to 1. Okay. So if you take define f of t like this, this is equal to 1 by root of epsilon n. This is epsilon n for t less than epsilon n and 0 for t greater than or equal to epsilon n. Then norm of f is equal to integral 0 to 1 mod f of t whole square whole raised to 1 by 2. And this integral you can split it from 0 to epsilon n and then epsilon n to 1. Okay. So from 0 to epsilon n, its values norm of f of t square, therefore this whole square plus epsilon n to 1, 0 whole square d plus. Okay. And here this value become root of 1 by root epsilon n square is epsilon n dt, and this is equal to 1 dt, and this is same as t within the limit 0 to epsilon and epsilon cancel, and final value is 1. Therefore here norm of f equal to 1. So for this function p epsilon n f is equal to norm of p epsilon n is equal to f is equal to 1. How? This is square is equal to this one, and this is same as this one. There is no need to write this all these things. I mark this as in square bracket. Okay, just for clarification, I write this. Okay, so this is equal to 0 to epsilon n like this, and finally we get same thing. Okay, norm of p epsilon n is f equal to 1. Thus we get the existence f belongs to L to 0, 1 such that norm of f equal to 1, and for this f p epsilon n f is equal to 1. Okay, therefore norm of p epsilon n is equal to supremum of norm of f equal to 1 and norm of p epsilon n f, and which is equal to 1, because norm of p epsilon n f is less than or equal to 1, less than or equal to 1 for every f with this one, and for that f we have already defined this f, this value is equal to 1. That means supremum value is equal to 1. Therefore norm of p epsilon n equal to 1. Okay, this is equal to 1. That means p epsilon n minus 0 not tends to 0 as n tends to infinity. Therefore p epsilon n is not uniformly converges to 0. Thus we get p epsilon n is converges to 0 in the strong sense, but it is not converges to 0 uniformly. Okay, that means norm convergence or norm, that means strong convergence need not imply norm convergence or uniformly convergence. Okay, so just check out the result what we have. Okay, thus we get uniform convergence implies strong convergence, and strong convergence implies weak convergence. Okay, but weak convergence need not imply strong convergence. Similarly, strong convergence need not imply uniform convergence or norm convergence. Okay, that's all for today's class. Thank you.